Good morning, good afternoon, good evening, class. This is Mr. Arosena, and today I'm going to talk about derivatives of polynomial functions and derivatives of exponential functions. I will probably not go through the proof of why these rules work, because we did this in class, and it's a little tedious to do it all over again. So I will not, but I will have links for other people who have done the proof, so you can see for yourself that these rules actually do work. Okay, so no actual slideshow today, so I'm just gonna write them all out. So the first rule we talked about, we discussed this actually last week, but the first rule we talked about was derivatives of constant functions. So derivatives of constant functions. And this one should actually be fairly easy because if you recall, a derivative is really just a slope. I'm going to keep that in mind. Derivative is really just a slope. And again, by extension, because slope is rate of change of something, the derivative is really just a rate of change. So a constant function looks like this. F of x is a constant function. F of x is equal to c, just some number c. So c is a number. C, a constant number. Constant number. And as we know from previous studies of math, a constant number has what kind of slope? Well, constant number, if I were to graph a constant number is just a horizontal line. Well, just a horizontal line. So this is c. Here is f of x equals some constant number c. Here's, oops, don't need that. Here's c. Just a horizontal line. So the derivative of a constant function, and we'll call that f prime, different color, f prime of x, well, it's a horizontal line. What's the slope of a horizontal line? Slope of a horizontal line is 0. So the derivative of a horizontal line is just 0. Okay. Now, I should also mention at this point that sometimes the derivative is written not as f prime of x, but sometimes the derivative can be written as follows. F prime of x is what I usually write because it's faster and easier, but sometimes we use what's called Leibniz notation, and sometimes it's written like this. This is Leibniz notation. Okay, and what this basically means, this is how I always remember it. I don't actually know if it's exactly what it means, but this basically translates to derivative of f of x with respect to x. Okay, that's the top part translates to derivative of f of x, and the bottom part translates to with respect to x, or because it's d, you can always think of that as depending on x. And this is really only important, the dx is really only important when you start dealing with functions with multiple variables. So for example, if it depends on y, then we can go df of y, dy, instead of df of x, dx, and so on. But this is just another way of writing a derivative. Okay. All right. So going back to here, derivative of a constant function. The derivative of a constant function is just this. That is the derivative of a constant function. Okay. Derivative of constant is always 0. Okay, so that's good. Next, suppose we have a power function. So derivative of a power function. Derivative of a power function. Well, a power function has this form. F of x equals x to the power of n. Okay. And without going into the proof, it turns out that the derivative of this function, f prime of x, is equal to n times x to the power of n minus 1. Okay. You can prove this using the definition of the derivative. And if you are curious about it, ask me in class or watch the videos that I'll link in the description of this video. Okay, but this is the derivative of a power function. You basically take the n, so this is x to the n. N goes down front to give me x, and then it decreases in power. Okay, that's how it works. That's how it works. Alright, so from here, let us let's go through some examples of using the derivative of a power function. Okay, so example. Okay, so let's say f of x is equal to x to the power of 4. F prime of x would just be, I bring the 4 down, so it becomes 4x, and then this becomes 4 minus 1. So this is going to be 4x to the power of 3. Okay. If f of x was, let's say, x to the 7, then we do the same thing. Bring the 7 down, so f prime of x will be 7x, and then 7 minus 1, or 7x to the 6. Okay. Now suppose we have a function, f of x, because power functions don't always look like that. Let's suppose we have a function, f of x is equal to 2x to the power of 4. Well, what happens here? Okay. Well, turns out that we can do the following. We can bring the 4 down, as usual, so f prime of x will be 4, but then this becomes times 2, the power of x, and this will be 4 minus 1. Equals, this will be 8x to the power of 3, like that. Okay. So let's try another one. So f of x is equal to, that's f of x is equal to 5x to the power of 6. Okay. Take a moment and try it for yourself. You could even pause the video if you want. Okay. So we bring the 6 down, so this becomes 6 times 5. This would be x to the power of 6 minus 5. So this is when we get 30x to, whoops, that should not be minus 5, that should be a minus 1. Minus 1. 6x minus 1, so it would be x to the power of 5. There you go. That would be the derivative. Now, from here, we moved on to the following. What if we have a function, so suppose, and we have the function where the function is f of x plus g of x. Okay, and what is the derivative? What is the derivative of this? Okay, well, let's just label it big F of x. So we'll call it big F of x. Oops, big f of x equals that. Well, it turns out that the derivative of big F of x is equal to the derivative of f of x plus the derivative of g of x. Okay, and again, we proved this in class, and if you're curious, you can always ask me about it in class. If you really want to, just ask me, and maybe I'll put a video up of the proof later. But anyways, so if I have two functions together, the derivative ends up being just the addition of it. And the same is true if I have a function where it's one function minus another function. The derivative of this ends up being the difference between the derivatives. So f prime minus g prime. Okay, so we could actually, this is like I guess we could call this a sum difference rule for derivatives. Okay? So if I have a function where it's one function plus another function, the derivative is just the derivative of the first function plus the derivative of the second function. And the same is true for subtraction. And then you could actually chain this continuously. You could have like h of x, and then this would be plus h prime of x. If this was minus h of x, then you could have minus h prime of x. And you can chain on into infinitely. Okay. All right, so let's go through an example. So example. So suppose f of x is equal to 3x squared plus 2x to the 4 minus 6x cubed, like that. Okay. Now, even though here I just have a single f of x, you can treat this as 3 separate functions. So we'll call this one, let's do this one in red, we'll call this one f1, do this one in blue, we'll call this one f2, and we'll do the other one in this magenta color, we'll call this f3. Okay, so f1, f prime of 1 is going to be, well, I'll just take the derivative of that, so this is going to be 6x. Okay, so the first part of f prime of x is going to be the derivative of f1 prime, so this will be 6x. Okay, plus, then we take the derivative of f2, this will be 8x, and then 4 minus 1 is 3. Okay, and then f3, this will be minus, again, if you're forgetting what's going on, bring the 3 down, so it'll be 3 times 6. This will be 18x, and then we subtract 1 from the power, it will be 18x squared. Okay, and there we go. So this is the derivative of, so this here is the derivative of this equation. And again, we're just using the fact that if I have addition of functions, the derivative ends up just being the derivative of the addition of the derivatives of each individual function. And it helps with polynomials, especially if you just think of each term of the polynomial as its own separate function. Alright, let's do another one. Well, you guys can try this on your own. So, f of x is equal to 3x to the 4 plus 8x to the 7 minus 10x squared plus 3. Okay, so pause the video, give it a try for yourself. Alright, here's how it would go. F prime of x would be, so that would be the derivative of this. So derivative of this, bring the 4 down, so we get 12 times x, reduce the power, so it becomes 3. Bring the 7 down, 7 times 8 is 56, x to the power of 6, minus, bring the 2 down, 20, x to the power of 1, and this is a constant, and so the derivative of a constant is just 0, so we don't even have to add it in. So there you go. There is our derivative. That's the derivative. Alright. Yeah, I mentioned I was going to talk about derivatives of exponential functions as well. The only exponential function derivative we really need to know is what is the derivative of e to the x. So, because in calculus, I mentioned this way back in the beginning of calculus, that we like to work in exponential. Whenever we deal with exponentials, we like to work in exponentials of base e. Because in calculus, we define base e as a function that gives us this property. Derivative of e to the x is e to the x. So, so if f of x is equal to e to the x, then f prime of x is equal to e to the x. This is one of the neat properties of base e exponentials, and this is something that mathematicians define in the study of calculus, that okay, if I have an exponential function, this e to the x is going to be a function that has this property. Okay, and this comes from the fact that if I have any exponential function, f of x is equal to a to the power of x, it's shown that the derivative of any exponential function is the derivative calculated at 0 using the definition of the derivative times the original function itself. And we define e So e is a number such that f prime of 0 is equal to 1. Okay, that's kind of what our definition of e is. The derivative of e to the x is, the derivative of e to the x evaluated at x equals 0 is equal to 1. So this has a neat property that e to the x is its own derivative. Okay, and this makes life a little easier for us. So here's an example. Okay, here's an example. So let's say f prime, or it's not f prime, f of x is equal to 3 e to the x plus 2x squared plus 3. Well, f prime of x, well, 3 times e to the x, well, the derivative of e to the x is just e to the x, so this term doesn't actually change, it still remains 3e to the x. This one, calculate the derivative as you normally would, so it'll be 4x, and this is a constant term, so there's no, its derivative is 0. So there you go. Okay, so calculating e to the x is, or calculating the derivative of e to the x is fairly easy. Okay, and that's because we define e to the x as a number that gives its, or as a, a number that gives its own derivative in a way. Alright, so that does it then for what we talked about last week and the first part of chapter 3. The assignment is on the blog, or you can ask one of your classmates to help you out with it. Right, good luck, and if you have any questions, come see me in class.